All right, welcome back to the video lesson. Today we're going to be looking at slope ratios and angles of slope triangles. So here's a question that you want to be able to answer at the end of the lesson. What are some relationships between slope ratios and the angles of slope triangles? Now, you have heard of slope triangles before where you're given a line, you have to find a slope, but then we drew triangles to find our slope, rise over run, and we created these right triangles, right? We're going to come back to that here in Integrated 2. So in previous chapters, we looked at relationship between triangles, and we were trying to determine if they are similar or congruent. Now we're going to be focusing our attention on slope triangles, which you used in previous course Integrated 1 for linear functions. So here's an introduction problem, okay? This is a pretty interesting one to think about. Leaning Tower of Pisa. For centuries, people have marveled at the Leaning Tower of Pisa due to its slant and beauty. Ever since construction of the tower started in the 1100s, the tower has slowly tilted south and has increasingly been at risk of falling over. It is feared that if the angle of slant ever falls below 83 degrees, so this is the angle of slant, if that is ever lower than 83 degrees, the tower will collapse. Engineers closely monitor the angle at which the tower leans. With careful measuring, they know that the point labeled A in the diagram at right is now 50 meters above the ground. Also, they determine that when a weight is dropped from point A, it lands 5 meters from the base of the tower, as shown in the diagram. So then you may pause the video and read over this on your own if you need to. But first question I want you to try to answering is, with the measurements that are given above, what can you determine? Okay, so here are some hints to help you answer part A. You know that the tower is leaning, and then from point A, if you drop an object, that object is going to travel a vertical distance of 50 meters. So it's 50 meters above the ground to point A. And then from the base of the tower, the bottom of the tower, to where you drop an object, where you could drop, it's 5 meters. And we know that this is 90 degrees given by the diagram, and that's the angle of slant. Given these measurements, what can we determine? Of course, this is a right triangle. We can determine this one, which is a hypotenuse. And now the hypotenuse is pretty much the height of the tower, the length of the tower. So here, this is a right triangle. We can definitely find this length. This is where the tower is leaning, by using Pythagorean theorem. 5 squared plus 50 squared is equal to x squared. So then x is going to be a square root of that. And that's going to be approximately 50.25 meters. So that's going to be this distance of the height. Now the next question, this time, can you determine the angle at which the tower leans? Which is this one. Can we find this angle? If you say yes, then find the angle measure. How would you find that angle measure? In this case, not yet. I'm not going to say no because we are able to find it, just not yet. Okay? And later in this lesson, you will know, or you will learn how to determine the angle for this type of situation and many others. However, at this point, how else can you describe the lean of the leaning tower? And we're going to use slope angle, which we're going to talk about more. The lean over here, the angle, we're going to call that the slope angle. Okay, now the Leaning Tower Pisa problem was an appetizer. Now we're going into the entree of our course. This is the main one, 3-68. I put star next to it, patterns in slope triangles. So in order to determine an angle, such as the angle at which the Leaning Tower Pisa leans, thus leaning angle, You need to investigate the relationship between the angles and sides of a right triangle. And we're going to do that by studying slope triangles. Okay, so what the heck are we doing with these slope triangles? First, I want to have a slope triangle, and we're going to draw it with the slope ratio of rise over run being 1/5. Okay, so we call this the delta y, and then this is delta x, which is the run. And we're going to graph this on a graph paper, which is basically a line with slope of 1/5. And there we go. It's right there. What is the name of this triangle? This triangle with rise of 1 and then run of 5, this is a right triangle. Simple. Now, just quickly reviewing, the delta y is always going to be the vertical. Okay, the vertical, the height of the triangle. And then delta x is always going to be the horizontal. Again, delta y is 1, so then this is a 1. Delta x is a 5, so the horizontal distance is a 5. Now the first one's done for you. Now we're going to do part A. You're going to draw 3 new slope triangles, all different sizes, but along the same line. And we're going to label the horizontal length as delta x and the vertical length as delta y. So here's the one that I want to do. I can go all the way to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then go up to. That's going to be a vertical length, delta y of 2, and horizontal length, delta x of 10. I can do another one. What if I double it? Go all the way to 20. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, all the way here. But then the distance up here would be 4. So my delta y, the vertical length, is now 4. Delta x is now 20. I drew 3 slope triangles, which are the right triangles. Keep in mind, the right triangles with different sizes. Now the next question is, how do we know that all slope triangles are similar? How do we know that all 3 different triangles I drew are similar? Well, take a look. I had the smallest triangle, and this was a 90 degree with this being 11 degrees. And then I drew a bigger one, which was still a right triangle, but then it's sharing the 11 degrees. And then I did another one, a bigger one. That one was also 90 degree with 11 degree here. So you could say they are similar by angle-angle similarity. But what else? There's also side-angle-side similarity. Because the 2 sides that are given to us with the measurements, they are proportional. They multiply the base and the height by the same scale factor. 1 times 2 is 2, 5 times 2 is 10, or 1 times 4 is 4, 5 times 4 is 20. So you can also have side-angle-side similarity. And then now, since the triangles are similar, what does that tell you about the slope ratios? If all the triangles are similar, then what do we know about the slope ratio? This was a slope ratio of 1/5, slope ratio of 2/10, slope ratio of 4/20, right? Because it's always change in y over change in x, delta y over delta x. They're all the same. So then part D, I definitely want you to pause the video to try this on your own. But the question is, what would be the, what would be the horizontal length if the vertical length of another triangle, another similar triangle, was 100 units? Try this on your own, come back to check. So then let's look at part D here. Here's the original triangle that we started out with in the graph. Vertical distance of 1, horizontal distance of 5. But then if we change the vertical length to be 100, now what is going to be the horizontal length? Well, this is similar. So going from left to right, it looks like it's being multiplied by 100. So multiply by 100, you should have 500 as the horizontal length. Pretty simple. So now this is where we're going to take all this in and talk about slope angle. Okay, remember the Leaning Tower of Pisa, the angle of lean, right? From the slope triangle. We're going to now talk about slope angle, and this can get pretty fun. So let's first do part E. We're going to draw a slope triangle with the slope ratio of 2/5. Label the horizontal length, the delta x, label the delta y, and answer this question. Is the slope angle going to be larger or smaller than this one? Is this slope angle, which means this angle over here, this is a triangle with slope ratio of 1/5. If you make a slope triangle with slope ratio of 2/5, is that angle going to be bigger or smaller? So first, make up your prediction, but we'll look at it together. So this one, the original, the ratio of this slope triangle, the slope ratio is delta y over delta x, which is 1/5, and that's basically as a decimal 0.2. And that one has a slope angle of 11 degrees. So now let's do 2/5. For this one, the horizontal distance is still 5, try to make them the same, but then now the vertical distance is going to be a little bit longer, so then delta y is 2. So then this angle over here, let's see, now the slope ratio is 2/5 now, which is 0.4 as a decimal, and in that case, if the ratio is bigger, then slope angle will also be bigger. Okay, so ratio is bigger or higher, so then the angle, slope angle will also be bigger. Now, what if the slope ratio was 4/13? Can you draw a slope triangle with slope ratio 4/13, labeling the sides? And is that slope angle going to be larger or smaller? So again, this is a slope angle that we're looking at. And is that going to be bigger or smaller? Let's see. The slope ratio is 4/13, which is approximately 0.307. So if this was 0.2, now a 0.307 slope ratio is higher, so the angle will be larger. Now this one, next one, part G, going to get a little bit interesting. What if the slope ratio is 2/2? Then take a look. What kind of triangles do we have here? We have the vertical and the horizontal being congruent, and it's 90 degrees in the middle. So now we have an isosceles right triangle. So first of all, if we're looking at the slope angle right here, now we have a triangle with slope ratio 2/2, which is equal to 1. That's higher than the previous one, which was 0.2. So definitely the slope angle is going to be larger now, because now it's one whole. 2/2 is one whole. It's larger, so the angle will be larger. But then, this time, can you find the actual angle measure? Yes, you can, because this is an isosceles right triangle. We know that these two sides are the same, meaning these two angles must also be the same. 180 minus 90 is 90. So then if you divide it by 2, that's 45 degrees, which is for this angle measure. And this angle measure is also 45 degrees. Okay. So then H, I'm going to give you a moment to think about and answer this on your own. So we have a slope triangle with slope angle of 45 degrees. And I'll draw it here too. Here's a triangle with a slope angle here with 45 degrees. Now, what would happen to the triangle if the angle increased to 55 degrees? If that angle now increased to 55 degrees, then which will be longer, the delta y or the delta x? Make up your mind, come back to check. Okay, hopefully you had your answer. It's 50-50 chance. So let's see here. If this is 55 degrees, this is when it was the same, both 45 degrees. But now this increased to 55 degrees, which means this would be 35 degrees. And remember, we always said that the biggest angle is opposite to longest side length. So in this case, hypotenuse is the longest because it's opposite to the biggest angle, 90 degrees. But then now 55 degrees is opposite to delta y. Therefore, that one is going to be longer than delta x, which is opposite to a smaller angle measure. So then, now let's put all this together and talk about patterns. What patterns did you notice about the slope triangles with different slope ratios? There are tons there. There's a lot. First, from the very beginning, we realized that as the slope ratio gets larger, the slope angle, which we don't know the exact measure, but we know that it's going to get bigger. Okay, so that's one. Okay, and now you can also do the opposite. If the slope angles are getting bigger, then you can assume that the slope ratio would also be bigger. And this was the perfect example, right? As the slope angle got bigger, even the slope ratio, because this is now getting longer, which means this length is going to be longer than this one. This value is going to be higher than this one, right? This was 1 and 1. That means now this angle is getting bigger, so this is going to be longer than 1. Okay, so the slope ratio will get bigger. Another one, a very special one. What happened when slope ratio was equal to 1? We had a special triangle. We had first, if the slope ratio was a 1, we had a slope angle of 45 degrees, right? This was 2 over 2, which is a 1, and that gave us a slope angle of 45 degrees because it created an isosceles right triangle. And I'll give you a diagram here. Slope ratio is 2 over 2, which is a 1, and that means these two sides are the same, and that means these two angles are both 45, so this is a isosceles right triangle. Now the next two, this is the most important ones. Have you noticed that whenever we're drawing a slope triangle, okay, this is always going to be a right triangle, and the delta y, the vertical length, is always opposite to the slope angle. Have you noticed that? And I'm going to put 3 stars on this. Okay, delta y is always going to be opposite to the slope angle. That's really important. And then what about delta x? Delta x would be down here, and what we're going to say, it's always adjacent. It's always touching the side with delta x. It's always next to it. It's touching it. It's always adjacent to the slope angle, but also touching the slope angle. Please make sure you write that down and keep that in mind. So then here's a question for you. Given the 3 right triangles, or slope triangles, which I can call them, okay, I'm going to call this slope triangle or right triangle, doesn't matter. Oops, slope triangle. Find the slope ratio of each of these triangles and decide which of these should have the largest slope angle measure. Try it on your own, come back to check. Okay, so let's see. Slope ratio of the first one is 20 over 50, which if you check, that's 0.4. So this has a slope ratio of 0.4. This one should be 3 over 7, which is approximately 0.43. This one is a slope ratio of 4 over 4, which is equal to 1. So then here's a winner. This is a triangle with the largest slope angle. And again, we know that this is also an isosceles right triangle. So this is going to be 45 degrees. Bigger the slope ratio, larger the angle. Pretty simple. So now, problem 78 is the back of the handout, the entire back. please make sure you copy each of the diagrams for each part of the problem, okay? So then here, what we're going to do is we're going to determine the missing angle measure or the missing side length given information. For example, let's do part A together. If the slope ratio of this angle or this triangle is 5/1, delta y over delta x is 5/1, then what is the missing side length? The W. What's the missing side length? W. Now, the first thing this is testing you on is being able to figure out what is the delta y and what is delta x. So, reviewing, if you're given a right triangle with the slope ratio, delta y is always opposite to the slope angle, but delta x is adjacent to it and it's touching the slope angle, right? It's right next to the slope angle. It's the side that is touching the slope angle. So then here, the slope ratio is 5/1. So then looking at my diagram, I see that this side is opposite to my slope angle. So then this must be the delta y, and this is adjacent to it. That must be delta x. And since we all know that slope triangles are always similar, they're all right triangles, right? And we are looking at slope ratios. So then we can assume that this triangle is going to be similar to another triangle that has a slope ratio of 5/1. So what we can do is we can write a proportion. Since this ratio is 5/1, that should be the same for W/12. And if you cross multiply, you get 1 times W, which is W, equals to 5 times 12, which is 60. And I have found the missing side length. So if you think you understood this first part, then definitely pause the video and try B, C, D, and E all the way on your own. Please make sure that you identify the delta y and delta x correctly and come back to check with the video. And now I'm going to continue on to part B. So now, if the slope ratio of a 45-degree, which is that one, is 1 whole, what is the missing side length? This one's pretty easy. If that's a 45 degrees, that means this is also 45 degrees, remember? And we said it must be an isosceles right triangle. So then A must also be 13, right? The side length should be the same thing. But if you want to use that idea of proportion, that we know that the ratio of 13/A should equal to 1 whole, which is the same thing as 1/1. Cross multiply, A is equal to 13, which is the same answer. Part C. Now we're looking at a slope ratio of 22-degree angle. That's 2/5. So then where is the delta y? Delta y is opposite to the angle, so that one is delta y. And delta x is the 25. And you always write ratio as delta y over delta x. If you put delta x on the top, that's wrong. It has to be at the bottom, the denominator. So this would be y over 25 equal to 2/5. Cross multiply, 5y is equal to 2 times 25, which is 50. So y is equal to 10. Next one has a slope ratio of 68 degrees and slope ratio is 5/2. So then again, in my diagram, this is the slope angle. The side opposite to it is the delta y. So delta y is 30. And then the side adjacent to it is the delta x. So my delta x is the x. And we know that the ratio is 5/2. So it should equal. Cross multiply, 5 times x is 60, which means x is 12. We're on to the last one. The last one's a little bit more challenging because the triangle is like rotated upside down, whatever you call it. So first thing, find the delta y and delta x of this triangle. This is the slope angle. The side opposite to that angle, which looks like this one, is going to be the delta y. And the side adjacent to it is going to be delta x. So then my ratio is going to be x over 15 equal to the ratio of 1/3. That's what you should start with. Cross multiply, 3x is equal to 15, so x is equal to 5. Please, this is a very, very important concept that's going to lead on to trigonometry, which is involving tangent. So it's a huge concept in Integrated 2. Make sure you understand how to find delta y and delta x of any slope right triangle. And that is delta y opposite to the slope angle, delta x adjacent to the slope angle.